the timestamp and a sequence number, and the sequence number is again to just make sure it's all in flow in the same direct like count, and basically. And the timestamp kind of helps out a little bit more. So like when you are having a conversation, say for 10 minutes, and then like it happens there's like a lot of lag. If the packets reach you a little slower, there's a lag in your conversation. So with the timestamp in there, like we can actually compress the actual audio file, which could be like a 10-minute audio conversation like that you have on the phone call, could be compressed to like 8 minutes or 4 minutes or whatever. And we can even use that to like help out a little bit with like all the silence packets and like pull those things out. And the regular other synchron. So the basic architecture that we have is like pretty simple. Like we have two people talking on the phone, sniffer, capture all the packets. And if you're having like a conference call, or if you're having like multiple, like if this thing is, if the VDLDS is deployed on a central position where we can monitor all the conversations going on in the organization, then like we need to split it all out into different sessions. So what I started doing out was like started using dpacket. It's a Python library, dpkt. Yeah, whatever. It's there in the reference. So dpacket module, what I did was like split the packets, like first took the packet, took out the IP headers out, took out the Ethernet headers out, everything, all the UDP headers out, and then went into the RTP header, parsed that one, and then pulled the data out, and based on whatever the encoding type was that I showed in the previous one, like apply the encoding and on the entire file based on the sequence number, and then start doing. So I got almost till that point, and that's when I'm like, wow, this is really painful to do all this work. And then I realized like I had to do all the session splitting and everything. So like, I don't know if you guys have heard of this tool called NetDude. It's a Linux-based one. So like, and it was kind of pretty outdated tool. So like we kind of rewrote NetDude in Python too. So like I said, okay, you know what? Let's just start using that, and then like use that to split all the sessions in the packet capture. So start doing that, and then finally, it struck me, I should probably Google this up now and see if somebody else has done it. And fair enough, there are like a whole bunch of other people who have done the session splitting and spitting it out into audio files already. So that's when I said, okay, you know what, I'm going to use one of the common ones, which is like spread across like multiple platforms. And like that's when we chose Waipong and Orica are the two people that we chose like that we can use to parse for this one. Going further into this one, like after the session breaker, we have the audio. Currently, the way we deployed, at least for the proof of concept, was like my laptop was sniffing the traffic from my desk phone, and then like whatever the conversation was happening was getting spit into the local machine. And we basically were like doing like I had script which should like on a regular interval go through that, find where if there are new files over there. If there are new files, then like shove it into like our web server wherever is the master. If the master could be running locally or on a remote server, so we can transfer all the files over there and then do the further processing over there. And then like the master basically does the audio to the text conversion, and then like we have our own engines to detect the keywords and all the regular expressions to detect all the credit card numbers and stuff like that, and then dump it into like the display portal. So a little bit more details into like the actual architecture of our tool is basically we have the payload converter. So we have the payload, which is basically the white packets with RTP packets in there, and we convert that into a media, store it into a media database, then send it through all our transcribing engine where like it gets like we generate the transcripts for those, and then we go to the detection logic engine where we figure out if it's like a PII data or if it is like a different kind of like an insider leaks or curse words, or based on what kind of rule you want to apply to it, we run that against it, and then if there's an event generated, then we send it to the display portal, and then it gets parsed and displayed over there. And if you want to add your own custom signatures to it, because I'm pretty sure you would want to like add something which is more specific to your organization, and then those kind of things can be also done very easily. So some of the other things when we started looking into it, like how can we get the audio data out of the packet. So when we started looking at it, we first said, oh, Wireshark has its own the VoIP telephony piece in it, and let's just use that one. And then like we said, like, okay, detect the streams, dump it to a WAV file, and then see how that goes. And then like we had a little bit of falses in there, like things like if you are using like Microsoft Office Messenger, which also uses SIP and RTP to communicate, and then like those kind of started mixing in, and then like we had like other cases where like it'll be a same stream, but then like in the stream like there are like certain other control packets which goes through the RTP session. So those all things that we wanted to take it out. So deep packet, like I mentioned, that was the Python library that we used. Then VoIPong is like, again, you have like a live CD that's available from VoIPong if you don't want to use their source code to compile it and do it. And you can just install it, and that starts dumping out all the audio files. Then we have Vomit and Eureka and RTP break and RTP scan, RTP dump, and RTP play and can enable. All these guys can dump out voice audio files out of the packet capture.
So obviously a good portion of this is actually getting the audio to some type of form that we can parse through and pull that data from. There were a couple different architectures that we looked at, and a lot of work had gone into one or the other. Obviously looked at the ones that are very specific to the platforms in general. So Microsoft's Speech, OS X obviously has their own speak recognizer class built in. Really wanted to stay away from that. Anything that isn't that mobile really isn't that good. Obviously, there are a lot of companies out there that just don't use Windows or OS X, and you'd have to develop it completely separate from the others. Also, you know, there are larger companies out there now that use Linux as their main desktop, so you really need to target, you know, at least all three, if not more, of those particular platforms. The one in particular that I kind of went for was Sphinx. So there are multiple versions of Sphinx out there, each for different reasons. There's Sphinx 3, which is a completely C-compiled module that you can use to filter audio down to text. There's Sphinx 4, which is Java, which you can do the exact same thing, and it was built to replace Sphinx 3. I really started putting a lot of time into Sphinx 4. As a matter of fact, the demo was probably completed once using nothing but Java, or Jython, because that was the fastest way to actually interact with their system, and it worked very well. The problem that we ran into is, as we looked into this, you know, Java's really heavy. So it was a much better idea to try something else, and the same people that make Sphinx decided to come out with Pocket Sphinx, which is very light. It's for embedded systems. It gives you most of the same stuff. It's a little bit simpler, but it gave us a lot more avenues in the future. We weren't necessarily going to be stuck using something that had to deal with Java. We could have a C library that worked on Android, it worked on iOS, it worked on the iPad, it worked on Windows. So it kind of covered all of our bases all in one spot, and it works fairly well. As far as Sphinx 4 goes, like I said, I really got into this. I thought it was mobile, but not as mobile as I needed. And obviously it was easy to hide, and it was easy to interact with. It was easy to interact with because I could use Jython, and heck, that's Python. Everybody can do that. It was really easy to hide because, let's face it, everybody has seen Java just randomly take up everything on their system for no friggin' reason. So why not? Well, before really going into it, it turned out that we really wanted to kind of hit the mobile area, and that's where Pocket Sphinx is. I mean, it just really allowed us these future avenues to go through. I'm not really going to get into a lot of kind of how voice to text works. It's based on phones, and basically you try to determine what is being said based upon what the standard phone is, so what is being said at that moment based upon what was previously said and what should be said next. So you have harmonic models and you have dictionaries that break down words into syllables, essentially, that you try to match on, and then base that upon what's going to be said next, or probability of what's being said next, so your language model. As we go further, you kind of find that, yeah, it's possible to get a completely bad translation of what was said based upon who's speaking and what is actually being said and which language model you're using, and then kind of like how the audio has been transcribed. So the architecture that we use for the actually detection of the what is output, because as we put these WAV files in there, it's got to be of a specific format to get the most likelihood that it's going to transcribe what you want. So to kind of combat the issues that come with something transcribing poorly, we had to make the detection engine really customizable. So it's script-based. You can program something in Python, and it's in that text file. Well, you can do anything you can do in Python. Just make sure that you know what you're doing, and you'll be able to pull anything out. It takes a little bit more skill, but it's going to be custom, and you're going to be able to format it accordingly. It's also rule-based. Because it's script-based, it's easy enough to have a script there that all it does is pull a bunch of rules from a file that's regular expressions that you can match on, and then just defaultly kind of push it out there. So, you know, Joe Sixpack can take care of it. Nobody really has to be too bad of a regex ninja. It does have lower customization, but that's what you sacrifice.
So one of the deployment architectures, like I said, like we can put it on taps with the PBX system and then like start dumping all the conversations. Basically anything which is going through the wire basically gets converted into WAV file and keeps dumped into the local hard disk, and then we can send it out for further processing and reviewing and analysis. So that's one way of having it done. So like you just have to deploy this at like one location. The second option is basically having it as a distributor one. So like if you are actually trying to like specifically target just one particular person in the organization or like just few people, then you can deploy this agent on their box and then like have that agent just report to the master wherever you have it set up, and then like it's all possible to set it up via the config file. Like you just set the config to this is the master, and then it just reports to the master, which is in a remote box, and then it dumps all the conversations over there, like parses it, transcribes it, and then first it actually does the standardization and using the SOCs, and then it does the transcription, and then it does the detection logic, and then spits it out in a not so fancy portal at this point of time, but will be fancy soon, hopefully. And the other option is like you actually hacked into one of the boxes, or you have a node that you have compromised over there, then you want to transfer this whole agent over there and then have it report back to you. And that was one of the reasons, like he said, like we wanted to keep it very lightweight and smaller so that like we don't have to deal with heavy transfer of file both the ways, up and down. So like we can even have the master run on their machine, and it's very low CPU intensive, and you run it over there, get the output, and then send the parsed output to you, kind of thing. So before we go into the demo, some of the future work that we have decided was like thinking about is like to disguise this whole thing as an app, maybe as a weather app or something, which says like it needs internet access and needs like the speech recognition software to put in the zip code or something, that kind of thing, and basically listen into every single phone conversations that you have on your cell phone and be able to transfer like just the key things that we need from that one to our servers. So then the real-time obfuscators. So the other thing that we were thinking about was like right now it's like all like the audio file is being generated, dumped into the local disk, and then we do all the parsing. But we are thinking if we can do this more in a real time, then like we can actually like start like beeping out, or like whenever like you are giving out numbers or you're cursing or something, like you just basically beep the whole thing out, and or just simple thing will be like just to drop those packets and things like that, and inject and like add more packets in there or filter out certain packets specific to that. Some of our references, and